welcome back. This is chapter 2. Let me back up a little bit here in the PowerPoints. So we're continuing with our study of the sky patterns. And so chapter 2 really does bring us, if I can get back to it here, to taking a look at the night sky. So this is sort of our user's guide to the sky. And the what are we kind of summary at the end of the chapters, which I always like to mention those, is that we are along for the ride. And so these great astronomical cycles that we're going to be looking at today in chapter 2, we are along for the ride. So the Earth motion, and the Earth's motion around the sun, and how that gives us these patterns and cycles, daily and yearly cycles of the sun and the moon and the stars. And so chapter 2 is going to kind of give us a guide to the sky. So let's go ahead and get started on that. To start off, yes, the night sky and the rest of the universe as seen from our planet is sort of the rest of the sky. The night sky is, we look out into the universe. So the universe is all around us, and so all we have to do is look up and out, and we can observe the universe. And so here we are on a planet. That planet is very dynamic. It is always in motion in many ways, but we'll look at some of those motions. It rotates on its axis, so I have my little skewered Earth here, but we'll be talking about rotation and revolution. But it rotates on its axis, okay, and that gives us our day and night cycle, and it also revolves in its orbit around the sun, so revolving. And that is definitely going to give us a yearly cycle with the motion of our planet. So the sun, the moon, the other planets, the stars, and the galaxies have what we call an apparent motion. It appears that they are moving, but it's really the Earth that's doing the motion. That's really caused by the motions of the Earth with that rotation on its axis and the revolution around the sun, the yearly cycle. So kind of keep that in mind, that we are along for the ride of these Earth motions. So we can see several thousand stars just by looking at the night sky. Our observations can be summarized by trying to name some stars, these little groupings of stars. And so we'll start off by looking at constellations, these just groupings of stars or patterns of stars that we call constellations in there. So there's our word, constellation. So these are just patterns of stars as we look out from the Earth, from our perspective here on Earth. We look out at the night sky and we kind of see some groupings or patterns in the stars. In the past, you know, historically, people had a lot of time on their hands and they used the stars. They would create elaborate stories about the stars. They would think that they would see some sort of mythical beast or a heroine or hero, and make up stories about these. So a lot of this does kind of stem back to early Latin, Roman, kind of Greek cultures. And so also Native Americans had their stories and so forth. But constellations kind of originated in Babylon, Egypt, Greece, many thousand years ago. And some of those are still used. Some of those names are still used. But it's important to note that the stars are really not grouped in any certain pattern. These stars are not physically even associated with one another. They could be very great distances from one another. So it just happens to be our perspective from Earth looking out onto the night sky that we see sort of some of these groupings. So a loose grouping of bright stars. So these, of course, were visible by the naked eye. You know, way back 5,000 years ago, we didn't have telescopes that now help us to see some of the fainter stars, but these would have been the bright stars that you could easily see with the unaided eye, okay? And just groupings of them. They thought they saw some patterns in them. And also, it kind of stems from the Greeks and the Romans. Astronomy kind of got its start historically. And so northern kind of hemisphere viewpoints are what were described in ancient literature. And so the regions of the southern sky weren't visible to the ancient astronomers who lived in the northern, Europe area hemisphere. So what we were really identifying were the ones from northern hemisphere kind of perspective, those latitudes. But loose, just kind of groupings of stars, just how they appeared from our perspective. But we needed something a little more formal as we were getting into really narrowing down boundaries of these groupings of stars. And so in 1928, the International Astronomical Union, which is abbreviated IAU, we'll refer to that several times, established officially 88 constellations, okay, with clearly defined and permanent boundaries that would cover the entire sky, okay? And so you can look here, we've got, defined boundaries for each of our constellations, but some of those constellations you might have that overlap two of those boundaries. And so they just mapped it out into 88 official constellations. And so like I was mentioning, you might get a little asterism, so a little grouping of stars within a larger constellation. For example, I think of the Big Dipper, which maybe many of you have seen and witnessed the Big Dipper, which is actually part of Ursa Major, the Great Bear, the Big Bear. So Ursa Major in there. So the Big Dipper is just sort of a smaller part of the larger Ursa Major constellation. So that's known as an asterism. Okay, so sometimes we tend to look at smaller things like that. But some of these stars, like I mentioned, may be many times farther away than other stars in that same constellation. So they're really not physically bound to one another, but they just look like a grouping or a pattern from our perspective here on Earth. So kind of are lying in the same direction. Okay, so asterisms in there. So they did come up with an official way to name our stars within a constellation. Lots of common names are used, but the common names, even though they are used, don't tell you anything about the star's brightness or its location on the sky, okay? And so we needed a more formal way to name our stars, and so they've come up with a method here to identify stars by assigning Greek letters to the brightest stars in the constellation. And so the brightest stars, they use the Greek alphabet letters in there. Alpha would be the brightest star in the constellation, beta the next star, and so on, gamma, delta, and so on, using that Greek letters to approximate the order of brightness. And so when we talk about this brightness, they'll get into that here in a little bit. Brightness as far as how bright it looks to our eyes, sort of the apparent visual magnitude. So that's going to tell us, that designation of that Greek letter, it's going to tell us what the order kind of the brightness of the stars are within that constellation. Alpha is like the brightest, then beta, and so on. That's one part of it. The other part of the name is this kind of genitive, Canis Majoris. And so they give sort of this possessive or genitive form of the official constellation name. So Canis Major, a constellation on the sky. And so they call it Canis Majoris. So they put sort of that possessive or genitive form of the official constellation, okay, name, and then alpha or beta, so telling you something about the brightness of the star. So the possessive genitive name gives you the location on the sky. Okay, so an official name here of a star, the brightest star in the constellation of Canis Major would be Alpha Canis Majoris. Okay, so Alpha Canis Majoris. So that's saying that this is the brightest star in the constellation of Canis Major. So Canis Major is the big dog constellation. And its common name is Sirius. That's the brightest star on the sky. Sirius is that common name for that star. But Sirius doesn't tell us anything about the brightness of the star or its location on the sky. But the name Alpha Canis Majoris tells us this is the brightest star in the constellation Canis Major. And so it will tell you something about the brightness of the star and its location on the sky with this official naming system. And so that is used. And so yeah, Alpha Canis Majoris identifies the star, what constellation it's in, so its location, and clues about the brightness of the star. So a very nice naming system. So be sure you're familiar kind of with that. Okay, and a lot of these names, common names, are stemming from medieval, Renaissance kind of Europe, Latin or Greek languages that were used. Some of them got changed around a little bit. Aldebaran, the bright eye of Taurus, the bull, coming from the Arabic Aldebaran, meaning a follower. So Arabic gets thrown in as well for some of these names. So a lot of those common names are stemming from the early astronomers and what they named them. Okay, so the brightness of stars. This is allowing astronomers to kind of divide into brightness groups. And so this first one here, this magnitude scale, it's a brightness scale. It really stems back hundreds and hundreds of years when it was used, when we've actually added and extended some things as our technology, our use of telescopes, and that came into being. And originally, we didn't have telescopes, but so the way it is kind of configured is based on apparent visual magnitude, what the brightness of the stars look like from our naked eye. Okay, and that's a little subjective because something might look a little brighter to someone else, depending on how good your vision is, your nighttime vision kind of thing. But the way this is, the larger the magnitude number, the fainter the star on our scale here. And so the smaller the number on our magnitude scale, the brighter the star. So like a 1 or a first magnitude star would be much brighter than a 5th magnitude star. So kind of the higher the number got, the fainter the star is. So the larger your magnitude number, the fainter the star. So let's say, for example, a 2nd magnitude star would be greater than a 4th magnitude star. It'd be brighter than a 4th magnitude star. So the lower the number, the brighter the star on our magnitude scale here. And it's definitely apparent magnitude, as you see here. Hopefully you can see. You do have these PowerPoints if you're not able to see everything very well. They're on Blackboard for you. But apparent magnitude, and it's symbolized as little m, a lowercase m with a V. So apparent visual magnitude. Okay, so kind of the apparent brightness. Of a star. Notice that that's a lowercase m and a subscript of a V, standing for visual, visible light, okay, visual magnitude, what it looks like from the naked eye, apparent visual brightness in there. So it's apparent brightness, okay. We'll make that distinction because we will have a symbol where we're going to use a capital M and a sub V, okay, which would stand for absolute brightness. And so that will have more to do with the actual amount of visible light energy being radiated from the star, because apparent brightness here is, again, a little subjective because, you know, vision varies from person to person. But the absolute visual magnitude is kind of stemming from how much energy is actually being produced from and being fluxed from the star. Okay, so it's a little more precise type of measurement there, and that'll be something that we'll get to in our star unit. Okay, so that's something to look forward to. But yeah, on this scale here, Polaris, if you look straight up to the north, is kind of called our North Star in Ursa Minor, that constellation. Polaris is pretty bright, and then Sirius is even off, if you notice, to the negative side. So they actually did have to add some negative numbers to extremely bright stars. So the full moon, very bright. The sun, in the negatives they added. And then the naked eye limit is a magnitude of 6, okay? 6 magnitude is really about the extent or the limit of the naked eye vision that we can make out. Above that, then even fainter, we're starting to need telescopes and things, and here we are, the Hubble Space Telescope limit at about a 30 on this scale. So yeah, these other numbers were kind of added as our technology advanced and things like that. So that's the apparent visual magnitude kind of scale, the magnitude scale. Okay, but the 6th magnitude is about, you know, the limit to what we were able to make out. Okay, yeah, so apparent visual magnitude, M sub V. And so, as I was mentioning, this is how it looks to the human eye, naked eye. Very subjective, as we mentioned. And so, really what we want to be looking at to be accurate, we want to look at the flux. Just how much energy is actually coming from 1 square meter per second from the star's surface. And so, that'll be something in our star unit that we'll take a closer look at. More numbers to this as we got more information. Okay, so true output, this is just kind of subjective. So here we are, the sky and its motions. So we can kind of think back to the way the ancient astronomers envisioned from our earthly perspective of looking out at the night sky, and it does look like this dome of stars just kind of blanketing and covering the night sky. And so they believed that there was this great sphere that kind of encompassed and encircled the sky. We call this actually the celestial sphere. I brought mine here, the celestial sphere. So you may not be able to see that perfectly, but inside there's the earth, and then on the outside of it there's just this dome encircling, a sphere kind of encircling the earth, and then we're looking out from the earth's perspective and what we're seeing on the night sky around us. So there's many stars on here. Again, you may not be able to see it perfectly. If you're in lab, we'll be taking a look at these models a little closer. And some motions of the stars through the night we could look at. We could look at the motion of the sun throughout the year. So this is our celestial sphere, is what we talk about here. Okay, having having technical difficulties there. But that celestial sphere, a scientific model. What we're doing here on this, and we want to notice 3 important points: that the sky objects appear to be rotating westward around the Earth each day, and this is of course a consequence of the Earth's actual rotation, daily rotation, eastward, which produces our day and our night. Many places on here, the celestial equator, okay, that celestial equator basically separates this into, the north polar region and the south polar region. Kind of just divides that in half, but it's actually an extrapolation of the Earth's equator onto the celestial sphere, okay, with this model, okay. So that's the celestial equator, okay. Another term, zenith. Might not be able to see that too well, but zenith is directly above a person, no matter where your location is on Earth. That's called the zenith. Nadir is directly below your feet, again, no matter where you happen to be on Earth. So a couple little terms in there. Okay, so zenith, yeah, directly above you. And so, for example, what you can see of the night sky depends on where you are on Earth. So what constellations you can see are dependent on your latitude. Okay, where are you located on Earth? Okay, and also what season is it? Because as the Earth is orbiting around the sun, our viewpoint of the sky changes throughout the year. So we kind of talk about winter constellations versus summer constellations, and those will be different seasonally. Ones that we call circumpolar constellations, we can see those all throughout the year. They never rise or they never set. However, that will depend on what your latitude is. As I mentioned before on the constellations, mostly what we knew about them was from the northern hemisphere, because that's where Europe is, and the ancient Romans and Greeks were the ones describing it. But depending on your latitude, you'll see different circumpolar constellations. But the circumpolar ones are constellations you can see all year. So yeah, Australians see many constellations that North America doesn't. Australia is down under and in the southern hemisphere. So yeah, they never see the Big Dipper like we do. So yes, your location on the Earth latitude is what's going to kind of dictate what constellations and stars are going to be visible to you. And of course our sphere has all of those latitudes on it. Astronomers measure distances on the sky in angles, and I mentioned the angles in our first lesson when we began to introduce the parsec to you, and how that was a degree of an angle kind of thing. So units of degrees with subdivisions called arc minutes, and if you recall, there were arc seconds as well. So like 1 degree has 60 arc minutes, and 1 arc minute has 60 arc seconds, and so it has nothing to do with time, but it is an angle of a degree. And so we do talk about, how many degrees or arc minutes or arc seconds a star's location is. Okay, so precession, this daily kind of motion of the sky, Earth's rotation adds a second motion that can be detected over thousands of years. And so they're talking about here, I can grab my ruler here, how, the celestial poles and the equator were slowly kind of moving. And I did talk about how the Earth sort of had a fixed kind of tilt to it here. It's a 23.5 degrees tilt, permanent tilt, okay. But they do say that it precesses, or it wobbles a little bit over thousands of years. And so let me very quickly here try to show you precession. I brought my little, my little spinny top toy here, and kind of see how that motion is. So we're seeing that rotation, and you're seeing it sweep out a little bit of a circle, a little bit of a wobble in there. That's known as precession. Keep losing my models here. Gather everything back up. Okay, so precession, it moved kind of out of the scene there. But yeah, so that will change a little bit our perspective. So yeah, playing with a spinning kind of a top on there. That slow kind of precession can kind of change our viewpoint. But again, this is a very long, so like for us, the position of the location of Polaris, let's say, that's not going to be changing because this is a very long kind of a cycle that can happen. So the Earth's kind of precession, 23.5 degrees tilt to it. And currently that is pointing towards Polaris, okay? And that star we call the North Star, common name Polaris, okay? So that's something of a cycle that can happen, and it will precess, and that slow circular sweep, 26,000 year kind of cycle for it. So it's not that ours is going to be changing today kind of thing. But yeah, they have seen that precession over time. Okay, let's see, precession. Okay, so a couple cycles, and I've mentioned them already. Rotation, so the rotation of the Earth. Okay, so turning of a body on its axis. So we have our axis here, it's permanently tilted 23.5 degrees towards Polaris, right? And it spins on that axis, imaginary axis, right? Not actually a skewered Earth out there, but an imaginary axis. And that gives us our day-night cycle. Revolution means that the motion of a body around a point outside of that body. So the sun, okay? Let me grab that model real quick. Okay, so ignore our little moon there for a second. But here we have the sun, so a point outside of the Earth, okay? And so this is revolution. The Earth does revolve around the sun, okay? And that takes a year, so 365.25 days to make a complete revolution. So that's going to give us our seasonal, yearly cycles of what viewpoint we're going to see throughout the year of the sky on our celestial sphere, okay? And that will change up things for us in a yearly fashion, give us our seasons, okay? So a couple motions in there, and it really kind of makes everything appear to be moving westward. The moon, the stars, the sun always appear to rise kind of in the east and set kind of in the west on the sky. But that's really due to rotation. Revolution then, things that we see throughout the year, our viewpoint, what constellations we're going to see, what seasons we're going to have, a yearly kind of a cycle. So for example, let's say that we increased the, where'd my little Earth go? Increased by doubling. Let's say we doubled the Earth's rotation. So it's going twice as fast, okay? Rotating twice as fast. But its revolution stays the same. It's taken that 365 days to orbit the sun. What would that do to the night cycle? How would that change the hours of the nighttime? Okay. It would actually cut it in half, right? So if it was rotating faster, your nighttime would be half as long as it normally would be. How would that change the yearly cycle? It would not. It wouldn't have an effect on the yearly cycle because the revolution stayed the same, okay? But it would be kind of affecting the day-night time by having the day-night time. So, yeah, it really would not have an effect on the length of the year, okay? An annual, okay. So the annual motion of the sun, we want to kind of take a look at the ecliptic, okay? And so they're talking about sort of this apparent path of the sun on the celestial sphere. is known as the ecliptic, and I know you're not going to be able to see this very well. But I've got a little ball here, a little yellow ball, that is the apparent motion of the sun. We know that the sun does not orbit the Earth. So that's not accurate. Okay, so that's not accurate on this model. However, it's useful for us because it will give us a position along what we call the ecliptic. And so the ecliptic gives us positions of where the sun would be located along this throughout the year. So really what the ecliptic is a projection of Earth's actual orbit around the sun throughout the year, its annual orbit. So it's an apparent motion, but it's caused by the real orbital motion of the sun. So we have the sun, of the Earth, around the sun. And so we have this location along the ecliptic, little very important positions that we use to kind of depict our seasons, okay? So that ecliptic is the apparent path of the sun, okay? And what our seasons would be, there's a little section in there. I don't know how well you can see this, but this is in your book, okay? And it will be important for you to know those dates of your seasons, okay? Let me see if maybe I can get the camera to zoom in a little bit on this. Maybe. These dates are going to be important for us to pretty much memorize here. These are sort of the seasonal, and I don't know, that might not be any better for you, seasonal events, the vernal equinox we talk about, the summer solstice, the autumnal equinox, and the winter solstice. And they have specific dates, okay, where the sun, okay, is at a specific location on the celestial sphere, okay? And this is when we have certain seasons. And so the vernal equinox, March 20th, that's when spring begins, our first day of spring. June 22nd, summer, so summer solstice. September 22nd, that'll be coming soon this semester. Autumn begins, the autumnal equinox. And winter solstice beginning December 21st, winter begins. So make sure you've got those dates, and of course those northern hemisphere seasons. The seasons would be opposite in the southern hemisphere, so kind of keep that in mind. But the seasons are very much due to that tilt of Earth's axis, okay? That tilt of Earth's axis, because at some point throughout the year in Earth's kind of revolution around the sun, that brings the northern hemisphere of the Earth tilting closer, well, not really closer, but at an angle toward the sun, okay? And that's going to cause it to have very high sun angles and long duration of sunlight. And this would end up being our summertime. The northern hemisphere is getting most of the light in that angle. And then at other times, okay, the Earth appears to be tilted away from the sun, to where now the southern hemisphere is getting the majority of the sunlight and the northern hemisphere isn't. So that would be like our winter solstice, our winter time, but the southern hemispheres, that would be their summertime. So they are opposite in there. And so the amount of light, length of daylight, so duration, and just how concentrated is that. Okay, so do memorize those dates in there, because those will be some important dates, the beginning dates of our solstices and our equinoxes. Okay, so something very important to note, what the seasons are not from. It's not caused by the variation between the distance of the Earth and the sun. It is not. If we were using that as our premise, we would see that during January, when the Earth is actually closest to the sun, so the Earth in its orbit, it actually does get a little closer and a little farther away from the sun throughout the yearly cycle. However, it's actually closest to the sun, known as its perihelion, in January. So if we're trying to say, oh, it's because it's farther away from the sun that we have winter, well, the Earth is actually closest to the sun in January and farthest from the sun in July. So that is not the reason for the seasons. Okay, so two things are the reasons. Okay, so they are caused by the change in the amount of solar radiation being received, and so that sun angle has everything to do with that, and the length of daylight that the sun happens to be on the horizon. Okay, so we'll take a look here at the a summer solstice. So in the summertime, we have here's like the celestial equator, right? Look at that little dashed kind of line there for the path of the sun during the summer solstice, that day. Solstice means the sun stood still kind of thing. But the sun is rising more towards, so the person's looking south there, off towards the east, but more to the northeast is sunrise, okay, on the summer solstice. And the sun is getting to a very high noon sun altitude, very high. So you're going to get very concentrated beams of sunlight. Let me grab my light source here. So very high, very concentrated, if you can see from that angle, a high sun angle, very concentrated beam of light, versus a lower sun angle. See how that spreads out and diffuses the light? So that's not so concentrated. So concentrated high sun angle, diffuse not so concentrated low sun angle. So that sun angle, the solar altitude, plays a very big role in the amount of solar radiation, the intensity that we are receiving. Okay, so on the summer solstice, so you remember your date for the summer solstice, the June 22nd, in there. And so sun rising in the northeast, reaching a very high solar altitude, and the sun setting in the northwest. Okay, so that would be a summer solstice scenario. You have over 12 hours of daylight, so you have a longer duration of the sunlight, and you have higher sun angles, giving you a very concentrated amount of solar radiation. And so those two things combined give us our warmer temperatures for the summer, okay, season. Here at a winter solstice, we can see again the person's facing towards the south, and we get a sunrise here that's more southeast, okay, sunrise, looking at this very low noon sun angle, much lower sun angle, and we set more in the southwest. Okay, so the sun isn't in the sky as long. It's got a shorter track, so a shorter duration, excuse me. So the length of daylight's shorter. And then the sun angle is lower in the sky, and so that's giving you less intense solar radiation. So that all culminates into cooler temperatures. So a winter scenario, winter solstice scenario, okay, with the seasons. So that's the reason for the seasons. It's the change in solar altitude, changing the amount of intensity of your solar radiation versus the day length. So solar duration, okay, is the other factor on that. Those are the reasons of that. Okay. The seasons. They're talking about the evening star and the morning star, Venus, as sometimes called. Okay. So yes, looking along it goes in a little bit greater detail as far as the celestial sphere, when it's passing across the celestial sphere. What it didn't mention there was at an equinox, the vernal equinox. Okay, this happens twice a year, the vernal and then the autumnal equinoxes, those equinoxes. So equinox stands for equal night. So your duration of your day length is going to be 12 hours of daylight pretty much all across all the latitudes on Earth on the equinoxes, the autumnal versus the vernal equinoxes. Except for extremes at the poles, it would be a little bit different hours, but pretty much 12 hours, equal daylight, equal darkness on an equinox. But for those, and they have their various days, March 21st, the vernal, and September 22nd, the autumnal equinoxes. For those, you're going to get the sun rising due east and setting due west, okay, as opposed to being a little more northeast and northwest in the summer and southeast and southwest in the wintertime. Due east and due west on an equinox, okay? So it's really having to do with where we are located in our orbit, okay, the Earth's orbit. All right, so I don't know, let's see if we can do this. This would be get it just right, here we are, the summer solstice. So the sun's direct rays are beating down on the northern hemisphere. It's receiving the most intense solar radiation, the longer day lengths, and that would be our summertime, summer solstice. Now I know you may not be able to see exactly what I've got here, but now we're in our orbit where the Earth is neither tilted toward or away from the sun, and the direct rays are right over the equator. This is an equinox, okay? Equal daylight angles. The sun is rising in due east and setting due west. Okay. Then we come around and notice how, another 3 months here, that now the Earth is tilted away from the sun, and it's the southern hemisphere that's getting the most intense solar radiation. And so here in the northern hemisphere, that ends up being our winter solstice. So we're not receiving very intense. The rays of the sun are more diffuse. The length of daylight is shorter, so that is our winter solstice. And then we come around again, and we're in a position where, once again, the Earth is neither tilted toward or away. Okay, the direct rays are right over the equator, and again, it's another equinox. Okay, so throughout the year, because of that tilt, okay, but that's the reason of this tilt, it's changing our solar noon angles, so the highest that the sun will get on the sky, and the length of daylight. So sun angle and duration is the reason for the seasons, and it's all due to that tilt. So it has nothing to do with how close or how far away we are from the sun, and those actually vary not all that much to cause any sort of a difference in there. So next thing we talk about are the cycles of the moon. Okay, our only satellite, our moon that we have, it's orbiting eastward around the Earth, taking about a 30-day trek, 29 point something trek, to where the name moon actually is why we call our calendar months, stemming from the moon because of the cycle of the moon. Okay, so I have actually given you, because I wasn't too crazy about their image that they showed for that. So I have a handout for you that we want to make sure that you do receive. Probably get it on Blackboard for you. Let's see if we can bring that one up. But you will want to zoom out here. Learn your phases and the associated rise and set times for our moon phases. Far back as I can get with this, but these are our moon phases, the rise and the set times. Okay. Yeah, I'm gonna have to move this around a lot to help us see this. Okay. typically we talk about initially starting with a new moon phase in there. So the new moon phase, okay, actually rises at sunrise and sets at sunset, even though we can't visualize it from here, our perspective on the Earth. It's there, okay, but we just can't visualize it because the sun's not illuminating that side. Let me get over here. This is new moon phase. So the sun's not illuminating the side of the moon that's facing the Earth. Okay, this would be a new moon scenario. And we're here on the Earth looking out. And that black side there, it's not getting illuminated, so we can't see our new moon phase. But it would actually be rising at sunrise and setting at sunset is its cycle there. So here, is where, sunlight coming from here illuminating that side, but our perspective is here from Earth trying to look out, and we don't visualize it because it's not being illuminated. And then you go about a week later, okay, the moon's in its orbit, okay. I have to kind of tilt that, so I don't know how well you're seeing that there. Maybe I'll tilt it like this. So here it is, sun illuminating this side of the moon, right? But from our perspective here on Earth looking out, we just see the right half of the disk illuminated, okay? So all along through that middle of that week, we're waxing crescent. We're starting to see a little bit more, until we get up to the top there at the first quarter phase of the moon. So we're just seeing the right half of the moon illuminated. And your rise and your kind of set times for that, okay, the first quarter moon, it rises at noon and sets at midnight. So this is one that you're going to see throughout the day. So it's not that you always see the moon at nighttime. It's easier to see that way, but you can see it during the day. This would be one you could see during the daytime, okay, the first quarter moon. And then we trek along for another kind of 7 days in there. And all the while, we're starting to see more and more of the illumination. So we call that a waxing gibbous. So gibbous kind of stands for hump. And we're starting to see a little bit more and a little bit more of that until we see the full disk. Okay, so our perspective here, so it's illuminating the full disk, and our perspective here on Earth looking out, we do see the full moon, the full illumination of the disk. Okay, so that's our full moon. Its rise time is at sunset. So as our sun's going down, the moon is rising on a full moon, and it sets at sunrise. Okay, so the sun and the moon are like opposite sides. Okay, so one's rising, one's setting in this alignment like this. So we're looking out here and we see that full illumination. That's a full moon in this orientation like this. Okay, and then we're continuing on around, okay, to where we've got a scenario like this. See how they're kind of at a right angle to one another. But for you to kind of get the Earth perspective, so here we are on Earth and we're looking out at that arrangement, and we see the left-hand side, just the left half of the moon being illuminated. And we call that third quarter or last quarter, and sometimes you'll see that. But looking out, we see the left half, okay, of the moon. And so a third quarter will rise at midnight and set at noon, okay? So you might catch a glimpse of that, early morning, and then it's beginning to set at noon, and that's a third quarter, okay? So as the moon, and then of course we make it back to new moon, and so that is completing a cycle of about 30 days, about a week for each one of those to make its complete cycle, so the moon cycles. moon phases in there. And so do be familiar with your names of your phases, the major ones in there. Of course, we have waxing and waning, gibbous and crescents as you go, so waxing, crescent, and so forth. And then waning crescent, the rise and the set time. So be familiar with that. And kind of the position where it's located in association to the sun and the earth. Is it in a parallel, lined up, or is it in that right angle sort of geometry, okay, for those. So let's make sure that you do have those, okay. Okay, so I liked the little handout that I gave you better than what they're showing you kind of here. I just didn't like that one in the PowerPoint very well. Plus, it has the rise and set times on the handout that I gave you. Okay, now let's take a look. Well, again, I just don't like these PowerPoints very well because they're not really showing what the disk would look like very well in here. And so the one that I gave you does show which half of the moon is illuminated. Is it the full disk? Is it not at all? Or is it the right half or the left half? So I like that better than these right here from your book. Okay. So the moon always keeps the same side facing Earth. They're like synchronized to where the same face of the moon is kind of linked. So it is rotating. The moon is rotating, right? But it's staying very synchronized with that same face towards the Earth. So we really only see that one side of the moon as it does like the man in the moon. Some people talk about, some see a rabbit in the moon. Very creative things that people see in the moon. But yeah, so the changing shape of the moon as it passes through, it's produced by sunlight that's illuminating kind of different parts, and I was trying to show you that with my demo there. Okay. All right, let's see. Let's take a look at the eclipses. And so we'll be using those different positions, and I've got a drawing that might help us on this. But they're very spectacular sights to see. I don't know if anybody, hopefully you did catch the solar eclipse a couple of years ago when we had that, and we'll have another one in a few more years, 2024. We're due to have another total solar eclipse that we'll be able to witness here in North America, in Arkansas. We'll get even closer to the totality. Little Rock, I think, is going to be in the path of totality of that. Okay, so, and looking at our solar eclipse, okay, and you're going to get a solar eclipse at this kind of configuration. Okay, hopefully you'll be able to see this, I'm not sure. So this is a new moon phase, right? So we're looking out here from the Earth, and we don't see the moon. Of course, it's there, and the solar eclipse is definitely going to tell us that it's actually there because the sun and the alignment is just right. And this doesn't happen every month because the moon actually does have about a 5-degree tilt to its orbit, so it's not always perfectly aligned every month to get a solar eclipse every month. So that's not how it happens. But here we have the sun. Let's see if that's going to work. Hopefully you can see a round, dark circle being projected onto the Earth. So when we have this perfect alignment at a new moon phase, okay, and when it's positioned just right, the moon is blocking a little bit of the sun, and it projects the penumbra, so the umbra, that shadow, onto the Earth. And so it's pretty localized. That's why, you know, not each hemisphere gets to see it, or each location gets to see it when we do have this alignment. But then, of course, Earth is rotating through that umbra, that dark shadow that's being cast by the moon. So this would be a solar eclipse, and that happens during the new moon phase, if you get everything aligned just kind of right. So the sun's kind of being hidden, eclipsed by the moon. The moon's kind of in the way of it. I'll have some drawings there. But the umbra is the shadow, okay, that the moon is projecting, okay, onto the earth. And so sometimes you can get just on the kind of outskirts of that umbra, of the dark total shadow in there, and that's called the penumbra. So if you kind of are on the outer outskirts of it, it'll get a little bit dark, but it won't be total darkness. And you never ever want to look at the sun without proper solar filters, right? So your sunglasses aren't good enough for this during a solar eclipse. Yeah, you got to have the special glasses to be looking at that. Now, there's a time that you can get the moon. Sometimes it's a little farther away from Earth, sometimes it's a little closer, and so you can get what we call this annular kind of eclipse, where you're just seeing just around the edges. You kind of see, I don't know if I can get that to image, but just maybe you're just seeing a little bit of a ring of the sun around it. Because the moon's kind of apparent size tends to be a little smaller when the moon is at its farthest place in orbit, okay? The apparent size of the moon, the real size of the moon's not changing. It just appears to because of its distance from the sun and from the earth. And so you can get this little annular kind of eclipse. The moon's kind of farther apart in its orbit around the earth, and it crosses in front of the sun, but you get that little dark visible little part of the corona of the sun there. So quite interesting. An annular eclipse. Okay. Solar eclipse. Okay. And there's the annular eclipse. Okay. So you see the little ring of the sun visible around the disk. But it never becomes really total in an annular eclipse. Okay, let's see. Yeah, slightly elliptical orbit. And so that varies the Earth to the sun distance, okay? And so that diameter can vary a little bit, even though the actual diameters are not varying. Their apparent diameters are. Okay, and you could do a nice little projection a safe way. So if you don't have the fancy glasses, the solar filter glasses, you could just do a little pinhole in a piece of cardboard, have that sunlight come through, and then project onto another piece of paper. And here we have sort of the partial eclipse happening. So we all want to get prepared now for the 2024 total solar eclipse. But that's a fun way to project it, a very safe way to project that and get to watch the eclipse happening. Okay, so try to prepare for that. And this list is actually old, but they do have one in your book that's updated. Takes us through 2024, a little ways past there. So we are due for one in 2024. Okay, so that's coming. That's something to look forward to. And then the lunar eclipse. So here, this was the orientation of a solar eclipse, right? New moon. If we get the orientation of, okay, here we are on Earth looking out, we have a full moon. So lunar eclipses occur during a full moon. And this is our geometry, okay? Full moon phase. And so, if it gets aligned just right, and again, this doesn't happen every month because of that 5-degree tilt of the orbital axis here that the moon is going in with respect to the Earth. So they're not always aligned properly. But basically what's happening is, of course, the sun is in the way, right? And it blocks out the Earth, blocks out the moon. Okay, so the Earth is casting an umbra or a shadow onto the moon. Okay, I don't know if they got that one showing. Okay, so the sun is kind of blocking, the Earth is blocking the sun, right? And it's this shadow, this is the umbra, okay, that the Earth is casting outward. And the moon is like orbiting through that shadow when everything gets aligned just right. Goes through that shadow, and so you just sort of start to see the moon kind of changing colors, dimming, and it kind of gives this dusty kind of blood orange kind of look to the moon, coppery color as it progresses, yeah, kind of coppery colored. So from that kind of reflected sunlight out around the curvature of the earth, and so quite beautiful as well, with a lunar eclipse, okay, falling through there, okay, and you can see it. And this is you know, it can take several hours for the moon to actually go through it, right? But you can view these without any kind of protective equipment. That's actually very gorgeous when we can. You know, the moon's full moon, and then it dims and turns a coppery color, and then it comes back to the brightness, normal brightness. So it's actually quite beautiful to see that. Okay, so solar eclipses don't always occur at new moon, and full moon, you know, lunar eclipses don't occur at every full moon. And this is because of that alignment. There's a 5-degree tilt in the orbit, so we don't always get that exact alignment every single month. And I think they had a list of when we could possibly see some lunar eclipses from our location. And again, this is kind of outdated. I should have one updated in the book here. Your third edition of the book has some of those listed for us. Take a quick look at those. PowerPoints are a little behind. It's from an earlier edition book. They sent me the new book, but they didn't send me the new PowerPoints to go with it. So these would be some lunar eclipses down here of the moon, and the ones up there were for the solar. So for solar, we've got April 8th, 2024 coming up, and it tells you where it can be seen from. So there have been more, but we just can't see them from North America, where we are. Looking like maybe a May 2021 that we could see a lunar eclipse possibly in our area for the lunar eclipses. So a couple of that. Now I do want to draw out those positions for you of a solar eclipse versus a lunar eclipse. I don't know if I can get both of those all the way on there. Maybe. Just so you have your geometry down and what moon phase we're talking about. So here's the big old sun, right? Casting its illumination. When we get the moon, it's a new moon phase. It can block a little bit, okay, and create a shadow, cast a little shadow, an umbra, onto the earth. So a very small location. That's why not all places on earth can see that when we have a solar eclipse. And so that would be a solar eclipse. The moon's kind of in the way, casting a shadow, an umbra, onto the earth at a specific little location there. Lunar eclipse occurs at a full moon. So the full moon phase, right? So here's our sun illuminating. If we're here on earth, it would be illuminating the full disk, okay? But if the earth is in the middle here, okay, at that geometry for a full moon, the earth is casting, when everything's aligned perfectly, a shadow, okay, and the moon in its orbit passes through the umbra that the earth is casting. And so you'll get where you'll just kind of see it trek across the moon, complete blocking, and you get the coppery kind of color. And then it passes through and you start to see the brightness of the disk again. And so that can be seen all over the world because the moon, you know, the earth is a lot bigger than the moon. So if you're just, you know, on the dark side of the earth, okay, you'll witness the lunar eclipse. And so that does conclude, I believe. Let's see what our PowerPoints have to say, if they have anything left in there for us about the lunar eclipses. No, that was it. So that does conclude chapter 2, the user's guide to the sky. And just remember that we are along for the ride. So astronomy is very much about you. The study of the universe is about you. And so we are in these astronomical cycles, the sun, the moon, and the earth as it goes through its seasons. So just keep that firmly in mind. And sorry about the technical difficulty on this video. The camera just kept quitting on me, so apologize for that. But if you have any questions, make sure that you do get with me, and I will see you next time. Thank you.